Hello, everyone.
Good morning.
Good morning. So I made sure all my 241 classes have access to all the videos of me teaching this week on chapter 4. So I put them up to make sure you actually watch them, because I recalled that I think it was this class I never did the actual what I call the fuzzy dice problem. So I did put that as one of the YouTube videos. So make sure you check that out. It's the problem where basically something's hanging from a rearview mirror and you can use that as an accelerometer. The videos this week, I think, are all pretty important. We're moving on to chapter 5, even though I left that example off, but I wanted to make sure all of you knew that I gave you those for the reason that I wanted you to see all those examples. There's a lot of other examples you can do. Of course, if you're doing your homework and you started your practice test, there's a ton of them that are important. What we're going to start with today is I'm going to start talking about how friction behaves, and you might want to actually, do something yourself on this in terms of the demonstration I'm trying to show you. If you have like a rubber calculator cover, something that's sort of tacky and sticky, so you could, or calculator, I said calculator, I meant cell phone. So if you lay your case down and it sort of doesn't easily slide, that's a good thing to demonstrate with. Or if you have a calculator that has some rubber stoppers on it, good sticky rubber stoppers, that's a good thing. Otherwise, you just take something like a little more heavy, like a book or something. But what I'd like you to consider is when you push on an object, you're going to push, like say it's on the tabletop like this, and I give it a push to start it. And what you'll notice is there's a little bit larger force required to get it going than the force required to keep it going. So when you actually start to push, you push a little bit harder, you push a little bit harder, and then all of a sudden it'll allow you to move, and then you feel it like decrease. And that's a very important thing, and it teaches a lot of stuff. For instance, it's one of the reasons that your meteorologist every winter will tell you, if you go into a skid on the ice, turn into the curve. Basically what's going on there is your tire connection with your road, or in the case of ice even, the tire's not moving with respect to the road. It doesn't seem like that, but if you work out the relative velocities, you'll see that is exactly the case. Because you can imagine, for instance, let me pull this sheet off and show you on another sheet. So let me turn on the document camera real quick and start to explain that. I didn't ask, does anybody have any questions before we get started? Let me go ahead and do that just in case. Well, you're welcome to save them afterwards, because we only have a 15-minute class, so it's not a problem. And I don't have something immediately after it today. Well, should probably check that. I don't think I have anything immediately after it today. Now that you think of it, I'm thinking maybe I do. Anyways, but either way, it's good. I got ample time at the end of class. So what I'm going to do now is turn on my document cam and show you an example about a car tire. Okay. And there's some reason for doing this, is because we're going to use what we learn about friction to make sense of why the meteorologist tells you to turn into the curve and exactly what he means by that. So if you imagine a car tire, okay, so let's just imagine for a second that's a car tire. So here's a bumper. Evidently, it just became a Monte Carlo. So anyways, if the car is actually going, let's say 60 miles per hour, okay, then I think you'd agree that the center of the wheel, that's the velocity of, say, the axle with respect to the earth, is equal to positive 60 mph. That makes sense, right? The center of that axle, the center of the axle, and therefore the center of the wheel is moving at 60 miles per hour because the car is going 60 miles per hour. Now, if you imagine this car up on a lift like you have, I mean, and this is dangerous, you don't want to do this, but like a lift like they have in a shop where they lift it up, 6 or 7 feet off the ground so they can work under it. If you have that, I think you would all agree that the velocity of the top of the tire with respect to the car and the velocity at the bottom of the tire with respect to the car are both 60 miles per hour, but in opposite directions. So you'd say this is the velocity of the top with respect to the car. And this is the velocity of the bottom with respect to the car. And this one's negative 60 miles per hour. And this one's positive 60 miles per hour. Does that make sense to everyone? Okay, so let's find the velocity of the bottom with respect to the Earth. Okay, so the velocity of the bottom with respect to the Earth has got to be, remember, this and this make the outer indices. So I'm going to put bottom first, and I'm going to leave a blank, and then I'm going to say plus, and I'm going to leave a blank, and I'm going to put Earth over here. Now what I have is the velocity of the bottom with respect to the car, so I'll put a C there. Then that means I need the velocity of C with respect to the Earth here. Does that make sense? Now this is all a vector equation, but luckily we're dealing with one dimension, so it's really easy. So I see that the velocity of the bottom of the car, or excuse me, the bottom of the tire with respect to the Earth is the velocity of the bottom of the tire with respect to the car, which is negative 60 miles per hour. And velocity of the car with respect to the Earth is positive 60 miles per hour. Oops, I don't know why I did that. So I'm going to turn this into a 60 miles per hour. And you see that, lo and behold, the bottom of the tire has zero velocity. It's a deep thought, right? Hopefully y'all knew it, but that sort of has to be the case, right? If it wasn't the case, you'd be spinning out. That's what happens when if you have a car that's powerful enough, let's say not a Honda Fit and not a Ford Focus or something like that, and you nail the accelerator really hard, then the tire friction isn't sufficient to hold up to the force that the tire is willing to put out. Therefore, the tire slips, and that's called a spin out. Other than that, there's no motion between the bottom of the tire and the road. And in fact, another neat thing, and this is sort of what's potentially dangerous about not having mud flaps and wheel wells in your car. For instance, if you had cars that were mounted, let's look from the front like this. If you had tires mounted like this, you could really get hurt with hanging your elbow out the window. Because that tire up top, notice we'll say the velocity of the top of the tire with respect to the Earth is equal to the velocity of the top with respect to the car plus the velocity of the car with respect to the Earth. And in this case, you see it's 60 mph plus 60 mph. So this object's actually flying up at 120 miles per hour. If you're on the side of the road with these tires like this, that rock can hit you at 120 miles per hour. If you're in the car, it can still hit you at 60, which is pretty damn fast, right? So that's a neat thing. Now that we know that, though, we know that the friction between the bottom of the tire and the top of the tire, or excuse me, the bottom of the tire and the road, I don't know where the top came from. The friction between the bottom of the tire and the road is what we call static friction. So what I was telling you earlier about take a calculator or a heavy book or something like that, and I suggested that you take it and push it along on the table on a smooth tabletop. And hopefully what you'll find out is that to get it started, and you try to use as light a force as possible, like the tip of your pinky, say, and just push it and it doesn't move, and push it a little harder and it doesn't move, and then push it harder still, and then finally it moves. But then after it starts moving, I think you'll find that the force decreases. So y'all should probably try that right now with something that you have, whether it be a phone. I had to turn mine face down because I've got, of course, my Baby Yoda pop socket. You can't have a phone without Baby Yoda on it somewhere. So, so anyway, you guys do that with your calculator or whatever. And what that tells you is that you can make a graph of friction versus, let's say, the normal force, and what you'll get is a neat relationship, just like the one shown on page 114 of your textbook. So this will be the friction force. Notice I'm writing it with that script. Oh, never mind. You're not noticing it at all because I'm not looking at you're not looking at the document game. So this would be the friction force. Why is it not going, darn it? Everything's moving super slow today. Like Zoom is taking forever. I click a button and it waits forever.
You're muted, Professor.
All right, my Zoom crashed. Can y'all hear me now? All right,
Yeah.
sorry about that. I don't know
Yes.
what happened on your end, but I disappeared. So I had to restart the meeting, I guess. So as I was showing you before with my notes, I showed you that the velocity of the top of the tire with respect to the car was plus 60. The velocity of the bottom of the tire with respect to the car is minus 60. And that's when the car is up on a lift. Okay. Now, when the car is actually going 60 miles per hour on the road, then only the velocity of the center is the positive 60 miles per hour. And what I tried to do is show you that the relative velocity between the tire and the road is zero unless there's skidding or getting a wheel, that sort of thing. So I showed you that the velocity of the bottom of the tire with respect to Earth turned out to be equal to the velocity of the bottom of the tire with respect to the center plus the velocity of the center with respect to the Earth. So I got minus 60 plus 60 gave me zero. That showed zero relative velocity between the bottom of the tire and the road. The top, on the other hand, gave us 120 miles per hour. I never actually wrote that answer, but it's 120 miles per hour with respect to the road or Earth. So someone on the side of the road, if a tire were to sling a rock out from the top of the tire, like on this type of car, then that rock could hit someone on the side of the road at 120 miles per hour, which is pretty dangerous. If it hits you, being in the car, you're already going 60, so it's only going to hit you at 60, but still 60 mile per hour rock hit is not very cool. So that's what we covered, and I'm only doing this rehashing that specifically because I think the recording died and they're not going to tack it on the end. It's going to be on a new recording. So the other thing was I was talking about with you giving a push to an object. Initially, it takes a larger force to get it started. And then once you get it started, the force actually quickly falls off. And in fact, if you make a graph of that, where this is the friction force and this is the force applied, what you'll see is that the force goes up, 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 up until it actually moves. Okay. And then it drops straight down. And then there's a constant force, more or less, that's going to be applied. This is called the static friction. And that's supposed to be perfectly level. I didn't draw it perfectly level, but that was by accident. This is basically F. Excuse me, I said static there. I was thinking about the other one. That was not supposed to be static. Please, everybody, correct that real quickly. Heck, I might as well correct this crappy graph while I'm at it. Oh. Okay. So now my attempt to draw a level line. Yeah, that's a little better. That's F kinetic. Like kinetic energy, like kinesiology, like a lot of different words you've heard before with that stuff in it. That means the for the friction force of motion. This, on the other hand, is F max. And F max basically tells you that the friction force is less than or equal to the static coefficient of friction, mu sub s, times the normal force. The kinetic friction, on the other hand, is equal to mu sub k times the normal force. So what I'm saying by this less than or equal, don't let that confuse you. It's actually supposed to be that. And the reason why we use that is we want you to realize that friction only acts up until as strong as it can. It doesn't just randomly push an object to the right. So right now, the static friction on this pin is 0. And if it was equal to mu static times the normal force, and I wanted to push it that way, the pin would just take off like this all by itself. So what that inequality is saying is it's going to supply a force as long as it can until that force is exceeded, at which time it only applied that force, and that's the mu static coefficient times the normal force. This is the reason that we spent last class, or last 2 days of class, teaching you about the normal force, because in order for you to apply the equations regarding friction, you have to understand how to calculate the normal force. Okay, so let's start off with a simple example, and I'm going to make it, we've done enough of the simplest of simple examples, so I'm going to make it a little bit bigger deal than the simple examples that often start off such a chapter. So I'm going to say this force F is 100 newtons. And I'm going to say it is applied at a 36-degree angle. Is that 36.9 we want? Yes, I think I want 36.9. Yes, 36.9 degrees it is. I always, for some reason, I'm really good keeping numbers in my head. I got a lot of random numbers in my head, but for some reason, this one don't stick in my brain very well. So it says 36.9. I know you probably can't read that with this great video or recording or whatever. This, on the other hand, has a mass of 10.0 kilograms. Actually, let's make it a little bigger. Let's make it 100 kilograms. Just in case, because I just put a big force here and I want to make sure I don't screw it up and give us a problem that doesn't make any sense. Okay. So now I'm going to lie this box on a surface. And I'm going to say that box has a static coefficient of friction of 0.50. Notice the static coefficient of friction has no units. And it has a kinetic friction equal to 0.20. And that's reality. The static coefficient of friction is always bigger than the kinetic, and that's why that box is so hard to push initially, but then once you get it started, it's easy. That's what this whole graph is about. That's what that demonstration that I tried to get you to do on your own was about. So what I want to do is calculate the acceleration A for this box, okay? So what I do is I draw a free body diagram, and I have a mass M. Well, actually, I don't want to write it there. I'll say my x-axis is this way. I'll say my positive y-axis is this way. I will say it has a force acting on it. Now you see why I didn't want to put that M there. And that force is 100 newtons. And although I didn't draw it to scale, it's at 36.9 degrees. Then I have acting on it as well is a force in the negative y direction. And I think you guys know what that force is. It's called the weight, which equals m times g, assuming again that this is the mass m. Now you also have another force acting in the positive direction, which I'm going to use purple to indicate. And that's the normal force. And finally, we have one friction force acting this way, F, and I'm not going to subscript that S or K because I don't know. I mean, if this force exceeds the mu sub S times the normal force, then once you give it that force, it will reach a big enough force to overcome friction, and then you'll just be pulling it along, combating that friction force. Okay. But if that force is too small, then it will just hold back and not let the mass go forward. So in order to solve this, I still have to break this force up into components. Again, we have the special 3, 4, 5 triangle where this is 4, this is 3, this is 5, and this angle right here is the one we're dealing with, 36.9 degrees. Obviously, to make 100, I have to multiply by 20. And then that makes everything kosher. Okay. So now I can see that the X component is really adjacent to the 36-degree angle. So that's the 4 times 20, that's the 80 newtons. And I can see that the opposite component is the 3 times 20, which is 60 newtons. Okay. Now I can do my F equals ma. I'm going to say the summation of the forces in the y direction equals mass times acceleration in the y direction. And we're going to use our fact that, again, the box isn't bouncing vertically. So we're going to say that's acceleration is 0, and we'll call the x acceleration the only possible acceleration. So in this case, I'm going to see that Fn, which is positive, minus 980. because 9.8 times 9.8 times 100 is 980, and it's actually 980.0 newtons because I used 4 sig figs there. Technically, I have to use 9.8 since I only know that 3 sig figs. I'm going to call that one doubtful digit. And that seems to be the only things acting vertically. So I now know that the normal force, Fn, is equal to, what? Did I forget something? I did. Anybody seen the other vertical forces acting? I drew it over here. That's why I missed it. It's better really when you're doing these vectors to break them up in tail-to-tail formation, because then you can see it actually acting on the mass. And I completely skipped it for a second, but notice the 60 newtons there is acting on the object. And exactly, Matthew. So I've got to include that, and that's an upward force. So I'm going to say plus 60 point, that was, yeah, I can say that 60.00 newtons, and that's equal to 0. Okay, so by pulling upward a little bit, you can see I'm ultimately going to be decreasing my normal force. So my normal force is not going to be 980. When I pull this over here, it's going to be 980. When I pull this over here, it's going to be negative 60. So I'm going to get 920. So the normal force is 920.0 newtons. And technically, again, that's 1 sig fig too many. Now, the summation of forces in the x direction is a little more complicated. Just because I don't know if this force is big enough to compensate for the other force. Well, what I do know is the summation of forces is equal to mass times acceleration. And again, since I've already ruled out the y acceleration, we're just calling that a. So in this case, I have an 80 Newton force in the positive direction. And again, I probably could put a second digit on that decimal place just for good housekeeping. So 80 newtons minus the friction force. Now the friction force is going to be less than or equal to mu sub s times the normal force. Well, mu sub s is 0.5 and the normal force is 920. So the max it could be is equal to 460. Yeah, because that's 800 and this would be 120. Yes. So yeah, so that's 920. So yeah, 460 newtons is the maximum that can be. I've got an 80 Newton force here. And that's the only two in the horizontal direction. So I'm going to say, well, this is going to be equal to 80.0 newtons in the negative direction. And that's going to give me mass times acceleration, which is clearly A is equal to 0. Okay. So that's a way you can deal with it. There's a lot of different ways you could actually, say it's maximum of that and then figure out what it is, that sort of thing. By me using 100 kilograms, I made the friction force too large for this force to apply. And in fact, I ended up getting a acceleration that must be 0 because notice I put 80 here. Does everybody understand why I put 80 there?
Actually, you lost me a bit. Could you go through the last like 1 or 2 steps of that?
According to this graph, whatever force you apply to an object, the friction force will keep it. In other words, match it. This is the equation F max equals F applied, because it's like y equals x, in other words. So it's a perfect 45-degree angle. So until you get to this number, which is F max, which I calculated was 460 newtons, then the friction force is going to be exactly equal to the applied force. So in our case, we had the applied force was 80.0 newtons. And that means this is 80.0 newtons. And this force, of course, is 420 newtons. So that's why we got 0 acceleration. That's why I put the 80 in there. Does that make sense to everyone? Now, let's do example 2, and we'll see we can actually make it a little, it's actually less complicated, to be honest with you, but it's a little more reasonable. We're going to do the exact same situation, except now the mass is going to be a 10.0 kilogram box. The force on it will still be 100 newtons, and it's still going to be at 36.9 degrees. And my free body diagram is exactly the same, except instead of 980, it's going to be 98 newtons. Okay, so let's draw our free body diagram. I've got acting on it this force 100, and then of course that means I'm going to have a positive component of 60.0 newtons and a positive component of 80.0 newtons. And I'm also going to have a positive component of F sub n. And I'm going to have a friction force F, okay? And I'm going to have a weight W equals mg is equal to 98.0 newtons. Okay, again, I'm asking for the acceleration. So for this one, I'm gonna take the summation of forces in the y direction equals 0. I think y'all can figure out by now why it's equal to 0. And that's going to be Fn minus 980, or excuse me, 98.0 plus 60.0 is equal to 0. So the normal force is actually going to be what, 38.0 newtons. Now the summation of forces in the x direction equals mass times acceleration. Again, we already said the acceleration in y direction is 0, so I'm just going to call that a. But this time I know it exceeds F max. So in fact, what's going to happen is to get it started, you have to reach F max. You're going to have to basically take 98 times 0.5. And of course, that'd be what, 19. So you got to apply 19 newtons to get it moving. But once you've applied that 19 newtons, then all you got to do is fight basically the friction force. So the total force now is going to be 80 newtons minus 0.2 now, because we exceeded the 19. F max in this case is equal to 0.50 times 98.0 newtons. And that's equal to, of course, 45. That should be 46. Is that right? 45 would be 90, and then 98, that'd be 49. Sorry. 49.0 newtons. So we've got to make sure we exceeded that. Our normal force, our force that we're applying, thank you, Matthew. I hate arithmetic. So 80 newtons minus the actual friction force. Now that we know we've exceeded the maximum static friction, we know we're in the kinetic friction realm. So I just have to multiply again. Mu s was 0.50, but mu kinetic was 0.20. So I have to just multiply 98 times 0.2, which would be basically 9.8 times 2, which is 19.6. Right? Yes. Okay. So minus 19.6 newtons. That's equal to 10.0 kilograms times A. So A, when I subtract 19.6, I basically get 60.4. So 60.4 newtons over 10.0 kilograms gives me 6.04 meters per second every second. Again, that's meters per second every second, and this is 6.04. Any questions on that? Now, the good news is when you take your dynamics class, if you actually have to take a dynamics class because you're going to be an engineering major, and not all engineering majors require dynamics, some of them just require statics. But when you take a dynamics class, they'll give you these little algorithms you can use when you have things like friction forces that go up to a certain amount, and they more or less make it where you just have to make sense of their algorithm and then memorize their algorithm, and then you'll be able to work these problems ad nauseum. We sort of like the creativity aspect, so we don't teach that algorithm. We just say, hey, this is the max that it's going to be. How do you have to figure this problem out? Because we'll do problems like having inclined plane Atwood machines, and you'll have to break the problem down and considering whether the block will go down this incline or up this incline, or the other block will go up the incline or down the incline. So you have to consider a lot of different scenarios. And we think that's part of the creative problem solving process that we want a physics major to be able to do. And actually we want all majors to be able to do that as well, but that's the way we do it in physics. Any questions on that? So remember, whenever you have a normal force, you can have a friction force. And whenever you have a normal force, of course, you also have something pressing against an object because the object has to reply with the normal force. So for instance, one of the often quoted problems that you'll solve, I'm not going to assign it to you, but it's a really cool problem to solve, is you imagine a ball with a BB rolling off of it. You could actually solve at what angle theta the ball leaves the surface. And the way you do that is you determine when Fn approaches 0, that's when it's actually going to leave and shoot off like that. Okay, so that's a neat problem that's within your capabilities by the end of this chapter, but it's not necessarily trivial. I don't usually assign that to my students, but it is definitely sort of a holy grail type problem. So if you can do that, you probably can figure out anything in chapters probably 1 through 10. Okay, any questions on that?
When you
Another
found the
problem you
force
might like
max,
too. I highly suggest y'all do this. This is really fun. Take an inclined plane and put it at an angle theta, and then put another inclined plane at an angle theta. So this part's actually absolutely horizontal. Well, yeah, I'm not seeing that. So we put an inclined plane at an angle theta with the horizon, even though my line does not look like that. And then I put another inclined plane mounted on a roller skate and put a scale on it and a person on it of mass m. And your job is to calculate the acceleration. You can assume all this other stuff is massless. The scale is way less than the skate and the inclined plane. This inclined plane is not moving, so that's not relevant. But you want to know what A is, and you want to know what the apparent weight is. So those are two really, really good problems. This one's way harder than that one, but this one's surprisingly hard as well. Okay, so something y'all can try on your own. I definitely recommend you do it at some point. But now I'm going to bring you to something else that we're supposed to learn in this chapter. And I want to do so by using a nice little circle that I drew earlier with a cheater thing, basically. Just a little sticker or something I had laying around. I don't even know what it's for. Oh, it's a tag from a fan, but it's a circle, so I used it. So anyways, what I'm going to do is I'm going to give you an idea about how to come up with what is the necessary acceleration to make an object go in a circle. And that is called the centripetal acceleration. But to do so, I'm going to first motivate you all to think about this. Let's say, let's consider a R vector. Okay, remember that R vector, that's the position as a function of time. let's say our R vector is equal to, and I'm going to use this notation so I don't have to write that crappy I, J, and K stuff. And actually, I'm only going to do 2 dimensions, so it's not even that complicated, but I'm just writing it this way because I want to. Okay, let's say I multiply R times the cosine of theta. Okay, so for instance, if you imagine this is the radius R and this is theta, then this would be R cosine theta, which is actually the x position, right? But I'm not going to call theta just a constant. I'm going to say theta is actually going to be 2 pi divided by some time t times lowercase t. Okay. And then my y component, I'm going to argue, is R times the sine of 2 pi over t times t. Okay. So let's do x comma y for the following times. Let's say, actually, I'll give me more room. Let's say over here. Let's say t equals 0. Let's say t equals t over 8. Let's say t equals t over 4. Let's say t equals 3t over 8. Let's say t over 2. Let's say 5t over 8. 3/4 t. And let's say 7/8 t. And then t. So what do you get for x comma y for t equals 0? Cosine of 0 is 1, right? And the sine of 0, of course, is 0, so I get R0. So evidently this object at t equals 0 is right there. Okay. Now at t over 8, notice the t on the top is going to cancel out with that, and I get 2 pi over 8, which is the same thing as pi over 4, which I think you recognize pi over 4 is 45 degrees. Okay. So in fact, this would be root 2 over 2, root 2 over 2, over 2 times R times R. So it's going to be right about here, root 2 over 2 R, root 2 over 2 R. And that's at t equal t over 8. Okay. Similarly, at t over 4, that's 2 pi over 4. That's going to be pi over 2, which I think you can suspect, as you will suspect, that pi over 2 has cosine of pi over 2 equal to 0, sine of pi over 2, of course, equal to 1. So you just get plain R. So we're going to get 0 comma R. And I think you can continue seeing what's going to happen. The next one will be here, then here, then here, then here, then here. And in fact, what you get is, I'll let y'all fill that out later. What you've got now is a radial vector, a vector that position vector for an object that's moving in time. Okay. And that object happens to be obeying a circular or following a circular path. And the period of that circular path is big T. Because by the time it gets back here, it'll be t equals t. And in fact, you can see the angle is really just that theta. That's why we wrote it that way. That's why this is R sine theta. And it even gives you the right signs and all that stuff. So we have R of t is equal to some constant R times cosine of, now I'm going to use a simplistic change of variables. Basically, I'm going to say, let's define omega to be 2 pi over the period. And that actually is going to be what we do when we do circular motion anyways. So we're just going to call this cosine omega t and R sine omega t. Okay. What I'd like you all to do is take the derivative of this. So let's take the dr over dt of this. Now, all you have to do, remember, this is IJK stuff. I and J are unit vectors. They have no function or anything weird like that. So when you take the derivative, they just pass through it like a constant. So the R and the I is just going to come out, and you're going to take the derivative of cosine omega t with respect to t, and you just have to use, of course, the chain rule. So what do you get for the I component when you take the derivative of R cosine omega t? Anyone?
So R sine and R cosine.
Negative R sine.
The R comes out in front. The I hat comes out in front if you want to. So I'm just going to write I'll write the I hat instead of using the brackets this time. So I take the derivative of cosine of anything, and the derivative of cosine of any particular quantity is a negative sign. Now I got to take the derivative of that quantity, omega t, with respect to t, and that's just omega. So I'm going to say this is R omega negative sine omega t. And this one, of course, the derivative of sine is cosine, and then the derivative of omega t is mega. So I'm going to say this is plus R omega cosine omega t, and that's the j hat. Now it turns out this v vector, which is really what derivative of position with respect to time is, this v of time has a magnitude equal to just R omega. Can y'all see why the magnitude of this vector is going to be R omega? So can somebody tell me why the magnitude is going to be R omega? Well, if you take the magnitude, that's equal to the square root of negative R squared omega squared sine squared omega t. And actually, I should notice that negative is going to disappear, so I'll just put that there. I was going to put parentheses around it, but then I started writing the exponents up here, so that made it not very helpful. Now I'm going to square the other one. It's going to be R squared omega squared cosine squared omega t. Of course, I got to take the whole square root of all that, but first I'm going to factor out a common factor of R squared omega squared. And then I'm going to do this sine squared omega t plus cosine squared omega t. Anybody know what the square root of sine squared plus cosine squared is?
1.
That's just a simple trig identity, right? So we end up getting just R omega. That's why that came out to be. Okay. So if you're going in constant, notice the magnitude is a constant. It doesn't depend on time at all. So this is constant velocity in a circle. And in fact, if you take the time to compute, for instance, what this vector is at time t over 8, like we did up here, you'll see this vector is actually pointing this way. Whereas the R vector, of course, points that way. Now what I'm going to do is, now that I've shown you how to do this, we've got this vector. V of t is equal to negative r omega sine omega t, comma, r omega cosine omega t, like that. What I want you to do is A, the acceleration as a function of time, is equal to dv over dt. And y'all can put it in brackets like that, or you can put it in IJK notation, doesn't matter. Everybody work that out real quick and see if we all agree on what you get. It should be pretty straightforward for you guys. Hopefully you all got something like that. This is the main part. As long as you got that, you're golden. Okay. The big thing I did is I factor out this to let you see, oh, wait a second, that's just negative omega squared times r of t. So what that tells you is this acceleration is pointed towards the center of the circle. And it isn't, and see, notice the negative means it's got to point in the opposite way that the r pointed. That means it points towards the center of the circle. And it only differs by omega squared in terms of the magnitude. We can now go back and figure out exactly what omega was. So for instance, we could say, well, wait a second, the magnitude of the acceleration, and this is going to be called the centripetal acceleration. A is defined to be a centripetal. You can see the magnitude of that is going to be r omega squared. Can everybody see that? Just like we did before, the r and the omega, they're going to become squared when you square all this, and then you get a cosine squared plus a sine squared. So that's just going to give you the identity 1 again. So it's just r omega squared. But remember, we defined omega to be 2 pi over t, right? So if you had another r there, so what I'm going to do is I want to multiply it by r over r. Then what I'd see is I'd get, so I just added this in here just magically, okay? But because I multiplied by r and divided by r, it's perfectly fine. So now I get 2 pi r squared. That r and that r makes you that allowed. And then I can divide that by t squared and then by r, because there's the r that I brought in, it was that little r. Does anybody recognize what 2 pi, well, let's write it this way. Let's say 2 pi r over t times 1 over r. Does anybody recognize what 2 pi r is for the circle?
Circumference.
Come on, y'all know what 2 pi r is regarding a circle?
Circumference.
Anybody here? Delaney, cadmium, somebody?
Circumference,
Professor, can you
hear us?
isn't
Yeah,
it?
maybe not.
Can you hear us?
Oh, yeah, there are a lot of muted people. How about, can somebody type it in? Somebody says I can't hear them, and so that might be the whole problem. Y'all are evidently saying the answer, and I'm just sitting here like a dum-dum. Okay, so yes, I'm assuming y'all said the right answer. Yes, this is a circumference. Thank you, Delaney. So yeah, that's the circumference. And if you take the circumference and remember that the t was the time we said it took to complete one loop, then I think you can recognize what the velocity or what the t 2 pi r over t is. Okay, so yeah, I think you see that's, and remember it's squared, don't forget. So that's v squared over r, because circumference is the distance traveled, t is the time taken to travel that distance. So this is really the velocity. And we found that the velocity, in fact, was a constant. So we know the average velocity, which is what 2 pi r over t is the true velocity. So we now know that a centripetal is equal to v squared over r. And that's an important discovery. That's something that tells us, hey, in order to maintain circular motion, something's got to supply a centripetal. That means center seeking, a centripetal force, and that force has to be equal to the mass of the object that's going in the circle times v squared over r. Okay, and that's a really big thing to learn. I can give you a hint. For instance, in the late 80s, it might have been the early 90s, but I think it was the late 80s. There was a story on 60 Minutes, and a person went to jail for this as well. But basically, he got the idea of doing these really large swings, and we still have people doing this now. They'll go out to, like Arches National Park in Moab, Utah, where recently 2 young ladies went missing, were found murdered. But that's normally not the scenario with Moab. It's really a quiet, awesome little town. But anyways, people will go to places like that, to the Arches, and then they'll hook up some rig and jump off of it and swing like this. And the other girl that's missing, by the way, was found in Wyoming, not in there. But anyways, they did find her body. That's terrible as well. But anyways, off those horrible, sad subjects, people will go around and build these swings, and you swing from these great heights, and it's really cool. Well, when this first started, one of the people going around doing it was like really into it, and he wanted to do it off the Golden Gate Bridge in San Francisco. So that's well, just for some perspective, that's a really high bridge, and it's so high that people often can use that for suicide. They got people that watch the bridge specifically to prevent that, because it's such a great height, you die when you hit the water. So their idea was, hey, we're gonna do this swing thing off the Golden Gate Bridge, and it's going to be beautiful. And the guy, having never been exposed to physics, didn't understand this fundamental principle here, this v squared over r. So he went to like a hardware store, and he had like 5 or 6 people, I think it was. He took their weights, and like, let's say their weight added up to like 2,000 pounds. And he found that he found some cable at like a Home Depot or some kind of store like that, and it was rated for like 2,700 pounds or something like that. He said, oh, good, I even got a safety margin. So that's what he connected or was going to make a swing out of. And he gave people like climbing harnesses, and they all attached into this, and they all jumped off the Golden Gate Bridge expecting to swing like this. Well, the problem is, you jump off the Golden Gate Bridge, if you were just sitting off the Golden Gate Bridge and you weighed 2,000 pounds, then 2,700 pound force capable cable will work just fine. But in order to swing off that, you have to have a cable that's strong enough to actually allow you to make that circular motion. In other words, you got to apply a force mv squared over r to maintain that circle of radius r, where v is whatever velocity you have at each instant. Well, that mv squared over r was quite a bit greater than the 700 or so pounds buffer that he gave himself, and it was really horrible. Like, they got down around 20 so degrees, the cable busted, there were boats under there, so some people ran into boats, some people ran into the water. One person was, I think, permanently quadriplegic, and the guy, of course, had to go to prison for it. But that was all because of the lack of understanding of physics. So if you're thinking about doing a swing, remember your force that you have to apply on a swing. Whatever cable or rope you're going to use has to be able to support the weight of the swinger, plus what their velocity will be at the highest velocity point, divided by, or squared divided by r. So you got to keep that in mind. And that's what we're going to use later to do calculations of how banked a curve needs to be. the time's up. You're free to go. I'm here if you have any questions, but until next time, I will see you then.
Thank you, Professor.
Can you hear us at all?
Hey, Professor.
No questions?
Can